Okay, so we will talk about the mixed design process of the concrete, and before that, we just need to verify some specific terminologies for the mixed design process. The first one is
Professor, you are left off with early volume change of concrete. I don't know if you want to continue with that.
oh, okay. Yes, thank you. Thank you for the reminder. Okay, great, good point. So let me finish that one first, and then we can start this one. All right. So early volume change of concrete, it was just only probably a few more topics to cover in this one, and then we can go back to the mixed design. So there are different types of early volume change. The first one is we call it the plastic shrinkage of the concrete. And that's when your concrete starts to shrink because of the evaporation, and you will see tiny cracks on the surface of the concrete. And it's usually around 1% shrinkage from evaporation. So shrinkage from evaporation. That causes cracking, right? And then there is a second type that we call it drying shrinkage. And that's happening after the concrete starts to set, so after setting. And that's if you don't do the proper curing, if not cured properly. So if you don't follow the curing process steps, you will have drying shrinkage, and that also causes cracking, right? So you don't want this types of cracks or tiny cracks happen on the kind of finished concrete surface. And then there is if you continue the wetting process continuously. So if continue the wetting process, then you will have very slight amount of swelling in your concrete. So if continue the wetting process continuously, you will have so very slight swelling in your concrete, and that's something that you don't want to have in the finished concrete surface or in terms of volume change. And then if you have non-uniform drying, so non-uniform drying, if you have some parts of the finished concrete is drying faster or exposed to the environment compared to the other parts of the concrete, you will have something such as curling happening in your concrete. So curling is happening again because of the non-uniformity in terms of curing your drying process. And then you have, we slightly mentioned that you will have a creep or a creeping process because of the changes in the curing process, and that's a long-term, so long-term gradual deformation. Long-term gradual deformation under sustained load. Under sustained load. And then that's also as a result of small strain that transfers load from concrete to steel in beams and columns, right? So even though it is a small strain, but transfers load from concrete to steel rebars. Steel reinforcement. Okay. And then there are some other properties such as permeability and also stress-strain relationship that I'm just gonna list them here. So permeability. This is important for when you want to have a permeable concrete with the ability to infiltrate surface water, but that's and it's a good practice to know that permeability is increased. So if you have the air voids on the x-axis, and you have strengths on this axis, compressive strengths. And then you have a second y-axis, which is permeability. Then there are two scenarios that with air voids, so I'm going to show the second axis permeability as a different color so that you know. So permeability. With higher air voids, you will have higher permeability, right? But the problem with permeable pavements or with permeable concrete or pervious concrete is that with higher air voids you will have lower strengths. So this is strengths, and this is permeability. So the higher permeability and higher air voids means lower strengths. And that's why they use only permeable concrete or pervious concrete only in parking lots or bike path pavements that they don't require a very high amount of compressive strength. And also there is the stress-strain correlation in the hardened concrete that we're going to talk about in the form of compressive strength. Okay, so and then the next thing that we need to know about the hardened concrete is testing of what type of test we use for hardened concrete. So testing of hardened concrete. The first is that we mostly do for pretty much all types of hardened concrete is compressive strengths of the cylinder or concrete cylinders. So compressive strengths or we call it F prime C of the cylinders, of the concrete cylinders. And that's basically once you have your cylinders hardened and cured for the same period, for some period of time. Sometimes it is 7 days, sometimes 14 days, and most of the time for the 95% of the strengths, you need at least 28 days. So you apply a compressive strength and actual pressure on the cylinder, and you apply the pressure until failure. And once you divide the stress, so compressive strength or F prime C will be the sigma of failure divided by the surface area. And that would give you the compressive strength. And we talked about we probably talked about how to prepare the cylinders in the lab or in the field. Oops, sorry. And that's similar to the slump test and the other processes that we talked about, that we fill 1/3 of the cylinder first. We use a rod to make sure that we have minimal air voids in the concrete layer, and then we fill the second 1/3 of the cylinder height, and we do the rodding 25 times only in that layers, and then we finish with the third layer and again rod for 25 times to make sure that it is uniform. A typical compressive strength range is usually between 3,000 to 5,000 to 6,000 psi. So typical range is 3,000 to 6,000 psi. And again, after 7 days, you will have, so 7 days, you will have 60% of the strength. And after 28 days, you will have, that's the 60% of strength of 28 days. And after 28 days, you will have 80% of ultimate strength. And the strengths after 7 days, they usually call it earliest strengths. That's you want to know how much your concrete, how much strength your concrete is gaining after the first 7 days. That's the earliest strengths. Okay, and then we talked about the standard size of the cylinders. It's 6 by 12 inch, and most of the time this is the standard, but there some testing procedures have adopted 4 by 8 samples that can be correlated to the 6 by 12 samples. Okay, the second test is called split tension test or a split tensile test. So a split tension test. And you most of the time you use the same machine, but this time instead of placing the sample vertically in vertical direction, you just place it down in horizontal direction, right? And you apply pressure on the side of the sample to know when it starts to crack and split into half, right? And that's called the split tensile strength. And that's usually 10%, about 10% of F prime C. And the tensile strength, or T, is if the load here is P, then this is the failure load divided by pi L times D. And in this case, D is the diameter of the specimen. L is the length. So if you look at it sideways, it's somehow like this. So this is L. And then P is the failure load. Failure load, or the amount of load that you apply until the specimen fails. Okay, and then there is a third type of testing, which is also very common in the concrete testing process. That's called flexural testing. Or flexural strength test. And this is important mostly for when you have fibers in your concrete, most of the time, and also for pavement applications. And this time, instead of a cylinder, you have a beam, small beam that, if you look at it sideways, you place it on two placeholders like that, and then you apply pressure on these two points through. So this is load. And then once you start the loading process, you will see cracks starts to initiate here at the bottom of the sample. And if you remember from your reinforced concrete class, the flexural strength is load times L divided by BD squared. And this is B. Depth of the specimen is D. This is L, length. And then P is the ultimate load until failure. And sometimes there's been studies that they have correlated the flexural strength to the compressive strength of the concrete. And if you look at the correlation, R is usually 7.5 to 10 times square root of prime C. This is in US customary units. US customary units. That's in PSI, right? So you can estimate the range of the flexural strengths, but the correct way to do this is to follow the ASTM standard to measure that in the lab. And then there are some other types of testing that are more unique and more specialized. Let me just mention these here, and then we can jump to the mixed design. Okay, so another types of popular concrete tests are non-destructive testing, and the reason is that we call these non-destructive is that for example, if you have a concrete slab or a concrete structure that's already, the concrete is already poured and cured and placed, once you want to do the quality control, you need to take a core out of a cylindrical core out of the finished concrete, and you're basically destructing the concrete surface to take a sample. So if you can do the concrete testing without destructing the concrete, that would be very optimal, and that would be very beneficial. That's why we call these non-destructive tests, or NDT. And non-destructive testing is not only for concrete. They use it a lot in other industries. When you have, for example, when you're manufacturing a metal part or any types of manufacturing parts, They do a lot of non-destructive testing to do the quality control of the manufacturing process. Or for example, in rail tracks, they do a lot of non-destructive testing to monitor the performance or initiation of any cracks before they happen. And they also have other applications in pavements and other types of any other types of structures. One of the non-destructive tests that we can use for concrete is called Schmidt or rebound hammer. So rebound or Schmidt. I'm going to post a picture of this device here, but it's basically a handheld device that there is a metered gauge on this device, and then once you apply the device on the concrete surface, from the rebound of reading of the the rebound reading, by reading how much rebound you have from from the device, you can measure the hardness of the concrete that can be correlated to strengths, right? So it's basically measures energy that's absorbed by concrete and you're basically measuring the hardness of the concrete that can be correlated to strengths. So hardness is not necessarily a strength, but it can be correlated to strengths. And this is a very some sort of an approximate test, and it's not accurate, and so not precise, and usually requires 10 to 12 readings in one area. Right? And then there is another device that's called Windsor prop, and that's slightly destructive. So Windsor prop. I'm going to post a picture of the device here. That's measuring the resistance of the concrete to penetration of a device. That's slightly destructive because you're slightly destructing the concrete surface, and it's also measuring the hardness that can be correlated to strengths. And you usually need to do 3 tests in one area to get the results. And again, it's not completely non-destructive, and it's slightly destructing the concrete surface. The next one is a very popular and very well known non-destructive test method that's called ultrasonic pulse velocity test, or UPV. And this is basically you are transmitting a pulse into the concrete surface and measuring the response or receiving the response of the pulse. And from the time that it takes for the pulse to transmit through concrete, you can correlate that with the modulus of the concrete and stiffness of the concrete. So this device, I'm gonna again show a schematic of the device here, and it's basically, so it's transmitting and receiving ultrasonic pulses. And then by measuring the velocity of the pulse of the receiving, which is the basic definition of velocity, distance over time. And distance, let's say if you have your concrete cylinder here, right? You apply the pulse here, and then you have a receiver here, and the distance is basically L, the height of the cylinder, and from the time it takes for the pulse to start here and receive here on the other end, you should be able to calculate the velocity. It's called pulse velocity, and from the pulse velocity you can see if there are any cracks inside or any disintegrities inside the concrete. So for finding cracks and delaminations or debonding in concrete surface, in concrete or inside the concrete that you cannot see. So that it's a very good test to measure those types of, or to find those types of discontinuities in the concrete. And then there's another test that's called maturity test. And the idea behind that is that the inside or the internal temperature of the concrete after you place the concrete is, because of the hydration process, the internal temperature is correlated to strengths. So if you can find, if you can measure the internal temperature in terms of maturity index, of the concrete, you can correlate maturity index to compressive strengths. So you can basically predict the compressive strengths of the concrete by just knowing the internal temperature. So what they do is, for example, if you have a big slab, it's already placed, you just embed some temperature sensors here. And by reading the internal temperature of the slab, you should be able to estimate the strength, and you should be able to see if the concrete is reaching the required strengths that you already designed for. And then there are some other types of some more advanced types of non-destructive testing that we don't need to discuss in this course. Okay, so that's pretty much the types of testing. And there are some other special types of concrete or alternative concretes. So let's talk about these a little bit, and then we can finally move on to the concrete, the mixed design process. So alternative concretes, alternative concrete types. One of the very famous ones is called self-consolidating concrete. And that's coming from the idea that, or self-compacting concrete, or they call it SCC. And that's coming from the idea that, if you remember, we mentioned that we need vibration after you place the concrete to make sure that the concrete is having enough covering around rebars, and it's filling all the gaps, all the corners. But in self-compacting concrete or self-consolidating concrete, it's a highly flowable concrete that you don't need to apply any vibration after placing the concrete. So it's a highly flowable concrete, highly flowable concrete, and which is not segregating, so with no segregation. Because most of the times, if you have a flowable concrete, if you want to have a fluid concrete, sometimes the aggregates start to segregate, but you don't need to, you shouldn't have segregation in the self-compacting concrete. And again, the benefit of this types of concrete is that it can spread, so it can fill the formwork, and also cover or encapsulate. So encapsulate the reinforcement. Without any mechanical vibration or consolidation. So without mechanical consolidation. And there's two more. The first one is called shotcrete. That this is when you spray the concrete into the surface. That's mostly for tunneling and excavation. That you need to spray the concrete, and there are two other types, that the heavyweight or lightweight concrete for special applications. And we talked about this one slightly before, the fiber reinforcement. So fiber reinforced concrete, that you have tiny fibers inside the concrete that can act similar to rebars, but not exactly like rebars. But in most applications, you can remove or reduce the amount of rebars by using fibers into the concrete. And the last one is roller compacted concrete, or RCC. So this is similar. This is very similar to asphalt, that you place the concrete on the surface and you use a roller to compact the concrete. And the very last one is called pervious concrete, that we already talked about, that has the ability to the permeability to infiltrate surface water. Okay,